Welcome to the fifth exercise for the lecture Adaptive Filters. In this video, we'll focus on subband processing structures. This video will have three sections. In the first section, we will review subband processing basics. Then we will have two comprehension questions and we will finish with a Python demo. So let's get started. When we talk about subband processing, we split our signal in several subbands, and we can look now at one subband to review the basics of subband processing. So when we have a subband index mu, and this mu is between 0 and m, where m is actually the number of subbands that we're looking at, then we can look at the following processing chain for each subband, and here we just look at our subband mu. So the first thing we do is we have to filter our signal with an anti-aliasing filter, and this is g of mu, and this filter has n elements. So n is the length of our anti-alias filter, and we do this anti-alias filtering because the following step is then to do a downsampling, a decimation. We denote this here with the downward arrow, and our mu is then the factor by which we decimate. And then we already have our subband signal, and we can then do some processing here. And then of course in the end we want to have a synthesis again, and we need to reverse the structure. So we do a upsampling with the same factor. And after this upsampling, we need to take care of the images in the frequency domain that are then created. So we apply a anti-imaging filter. This anti-imaging filter, we denote this here with the bar over the G to make it different from our anti-alias filter. And we say this has also a length of n samples. Okay, and this is then our full processing chain. And this is just one subband, and if we want to fan it out for the several subbands, we basically copy this entire structure here. So we take it from our input signal X, and we copy this structure here. I don't write it down. And then in the end, we just add all the outputs of our subband processing chains together, and we have our actual output signal of our filter bank, basically. So why is it actually beneficial to split the signal into subbands and do the processing there? Yes, we don't have to perform our filter updates as often, but of course we have then m channels in which we perform the updates. So this is not really the benefit. The benefit is actually then that the filters that we need to update, they also become shorter because of our downsampling. And this is then where we can actually save a lot of computational load. And we can take some simplifications when we look at the subband processing, when we want to go to efficient implementations. The first thing that we say that in every subband, we downsample with the same factor. So this R mu is actually just an R. And we say that the anti-imaging filter, we can get those by looking at the anti-alias filter, and we just reverse the element order. So G bar of mu is basically just G of mu in reverse order. And then another simplification we can make is actually that we don't really have a different filter for each subband, but every filter is based on a so-called prototype filter. So let's look what a prototype filter is. This basically means that when we look at our subband filters and the elements of the subband filters, and here I is our element index in the filter, then this can be broken down for every subband to our prototype filter elements, and our prototype filter is then just G here without a subband index, and we get the individual filters for every subband by then modulating this filter. And actually this prototype filter when you want to design it, you will want to design it based on the properties of the convolution of our alias filter and our anti-imaging filter. This is what was done also in the lecture. You looked at the properties of the convolution and then broke it down to what the individual filters need to look like. And when you have this prototype filter, you can then make a very efficient implementation. And this implementation is then what you saw in the lecture. That was the DFT modulated polyphase implementation. And what this is, we will see in the comprehension questions, and we will actually also work with this in our Python demo. So this was the quick review. Let's move on to the 2 comprehension questions I have for you. The first question is, what quantities describe windowing functions in the frequency domain? And for this, I want to look at a picture from the lecture. And here for this case, we compare 2 different windowing functions, and we look at the impulse responses of those 2 windowing functions, and then here at the magnitude frequency responses. And you see here on top is just a regular Han window, which was designed for a FFT size of 256, which we see here that we have 256 non-zero samples. And the other impulse response here is a prototype low-pass filter that was designed for filter banks that we saw in the lecture as well. And this has more non-zero samples. We have more than 600 here. We see this down here. And then when we take both of those impulse responses to the frequency domain, we see the magnitude frequency responses here on the right. And they have things in common, and they're also, of course, different. And we wanted to know what the quantities describing the windowing functions in the frequency are. And it's basically that we look at this, what we call the main lobe here in the middle. This here is the main lobe, and all those other ones here, those are what we also very often call the side lobes. And when we talk about a bandpass, then usually the main lobe corresponds to the pass band, and the side lobe should correspond to the stop band. And we look at the windowing function, and we are interested in how wide our main lobe actually is. So we're interested in what our bandwidth is. We can define this bandwidth as a 3 dB bandwidth or something like that. And when we then think about filtering, then it's also interesting what level here our side lobes, our stop band has, because this basically tells us what level our aliasing terms will have, because those are then frequencies that we do not want to have in our signal that we want to filter out. So this should be very low. And you see then when we look at the frequency response of our longer filter, that by making our impulse response longer and here maybe asymmetric a little bit, we're able to make everything a little bit sharper here. Our main lobe is not as wide, so we can achieve a better frequency resolution. And you also see that our stop band attenuation, so the level of our side lobes down here, it's extremely low here. And this we were able to achieve by making our impulse response longer. And that's also, like I've mentioned before, one of the advantages of the filter bank approach, that we can use windowing functions or filters with those improved properties here, and we couldn't use this with just a regular FFT analysis. The second question is, what is the DFT modulated polyphase implementation? And this implementation is just a very computationally efficient implementation of our analysis and synthesis filter bank structure. And here we can look at the analysis part, and actually we work some tricks in here in this implementation because we switch some operations around so that we can actually make it more efficient, and we use, of course, a prototype filter. And you see here first in the beginning that we first have a buffer. We buffer the number of samples that actually corresponds to the length of our prototype filter. And then you see here that actually after our buffer, we already have our downsampling actually before we apply the anti-aliasing filters. And that's actually one part that makes it efficient, that we apply the prototype filter at the lower sampling rate. And then you see here that we add certain samples, and we always add the M samples. You see here we have here the ways G0 and GM, and they're added. And if I had more here, we would add then 2M, 3M, and then when we go to 1, we add then G1 and GM plus 1. So we add them, and so that we get out of our N samples or channels, we then get to our M subbands. And you remember that we still have to actually modulate our filters so that we can actually have our separate band passes. And this we then do by this IDFT block down here, because the IDFT has exactly those modulation terms in the sum that we need. But because the IDFT has a weighting of 1 divided by the number of samples, and we don't want to have this here, we need to scale it by M. And this then gives us our subband signals in a very, very efficient way. And when we then look at the synthesis filter bank, there we also apply the IDFT, but here we then have to spread our subbands out again to N samples to N channels. So we use our first channel again for 0 and M and 2M and so on, like we saw earlier when we added. So this is how we spread it out again. And then those individual signals, they're upsampled and added to a buffer that is of length N. And we always pass the samples through, and in every rth iteration we add then samples. And our output sample is always the one up here that is the result of this buffer and processing chain. Both the analysis and the synthesis structure of the DFT modulated polyphase implementation we will now implement in our Python demo. This script actually closely follows the context of the lecture. So we will run the script with an input of a Kronecker delta, and this is what I have up here. And then the first thing we do is we load a prototype filter, and this prototype filter is again saved as a WAV file. And you can ignore the sample rate here. We have a length of 128. And then we set some other parameters, and in the lecture we worked with 16 subbands and a decimation factor of 12, so we have this here as well. And then I have a section for you where we do some allocation, and the allocation is not necessary because we can just override the values there, but the section is basically for you to understand all the dimensions that we work with, because we change between M and N and all those parameters. So I have some parameters here where you should then fill in the right dimensions, and those are the dimensions that we're working with. And the first one is our input delay change, so the length of our buffer that we saw in the analysis structure. And we then have our filtering with our prototype filter, so the weighting with our G's. And you remember we add there, so when you remember that, you should know what the dimension of that should be. And then, of course, the dimension of our subband vector should be clear. And this is, of course, the same as when we then transform out of the subband domain again. But we change our dimensions again when we then do our weighting again with the prototype filter. And you should also know how long our output delay chain is. And the output signal, this doesn't have to do with those dimensions. There we just put in the output of our entire structure for every sample. So this is just to save our signal. But then something I introduce for our implementation is a mapping matrix, because we need to code which samples are weighted by which weight of the prototype filter, which samples are then added, or how we basically spread our subbands again. And this we have in our mapping matrix. And your job is to fill this mapping matrix correctly. It's basically initialized as a 0 matrix, and you have to fill in ones in the correct positions. And if you're not sure how this should work, you will see this later on when we do the processing, how we apply this mapping matrix. But this is the first big thing you should do. And then we go here in our processing loop, which is of course sample-wise. And I already have the buffering processing here for you. So we put in always a new sample in our input buffer. And we also take care of our output buffer here. So we shift everything forward. And by doing this in the outer loop, we also implicitly do our upsampling later on, because what we have then now, we will only do every rth iteration, but because we do our shift here, our out buffer, on every sample set at our high sampling rate, we implicitly have the upsampling in here with the 0 insertion. Okay, but then of course, this next part we then do only every rth iteration, and the first part is then actually applying the prototype filter and adding the values. And you see here that I've applied our mapping matrix. So we multiply the mapping matrix with the input buffer samples, which have been element-wise weighted with our prototype filter elements. And when we then have that, we can then just simply go with this from this vector to the subband domain with our IFFT. But there's some weighting missing here. Fill this in, please. And then there's room for subband processing, which we will not do here. We will just transform right back. So this is what we do then here with the IFFT. I'm enforcing a real part here because due to some numerical problems somewhere, it might happen that we get a small imaginary part. So I'm just enforcing real numbers here. And then you should implement the rest of the synthesis. So you should do the weighting with our anti-imaging filter, and there you should use the mapping matrix again, but you need to apply it a little bit differently here. You saw how we used it up there, and you figure out how to do it down here. And then you need to mix the result into the output buffer. It's very simple. So implement this as well. And then we, from this output buffer, we always need to extract our current sample. And this we, of course, do at our high sampling rate. Okay, this is the actual processing. Then I have two plots for you. We will look at our magnitude spectrum. We will compare the magnitude spectrum of our Kronecker delta with our output. And we will look at the unwrapped phase, because we of course want our structure to be of linear phase, and we will analyze if it actually is of linear phase. Okay, now go ahead and fill out the script. I will now run you through the missing parts of the script, and I'll go ahead and implement it. Okay, let's start up here. Of course, our input buffer chain, it has to be the same length as our prototype filter. So this is n. But then when we do the weighting, we do an addition and we go down to the number of subbands. So this is m. And of course, our subband vector should be the length of our number of subbands. So this is m as well. And the same holds when we transform it back. But then when we do the weighting with our anti-imaging filter, we spread our samples out again to n. So this is then n, and the output buffer is of same length. So this is n as well. Okay, now we have the dimensions, and we can go ahead and implement the mapping matrix. And you see here that we put ones in certain positions. And the question is, where do we actually put the ones? What's the condition there? And you know, when we look at the first row in the matrix, then we should have a 1 in the first position. And then we want to add samples that are weighted by G0 and Gm and G2m. So the condition here is that we look at modulo, and when the difference between j and I, modulo m, that is 0, then we want to insert a 1 into our matrix, because this will then do the correct addition. Okay, so we have our mapping matrix. When we then go into the processing, this here is very simple. In the analysis part, we need to weigh our IFFT with m. Very simple. And when we do the weighting down here, we apply the mapping matrix again. But here we need to transpose it. So we say numpy transpose of mapping. And we multiply this with our transform subband. But here we haven't done any weighting yet, we just have fanned out the samples. So we do a multiplication. This is of course element-wise. And we do this with our image filter samples. Okay. And then how do we get this into the buffer? We need to add it to the buffer. We cannot replace. So we say to the output buffer, we add the weighted image. Okay. And then the output is then just simply the first value that is in our output buffer. Okay, now we have everything. Let's go ahead and run it. We see here the magnitude spectrum of our input in blue and of our output in orange. And as expected, the magnitude spectrum of our Kronecker delta is flat over all frequencies. Our output is not, but it's close. So we almost can reconstruct our Kronecker delta. We just have a slight variation. It actually looks bigger in this plot here. It's less than 1 dB to both sides. And this is more or less the result we saw that was achieved in the lecture as well. So this verified that our structure is working. And then when we look here at phase, we see the phase of our Kronecker delta, and we have the phase of both our anti-alias and our anti-imaging filter, and we have the phase of our output. And you can see that the individual filters, they're not of linear phase, but our output is of linear phase. And this is because the prototype filter was designed correctly, and we use the mirrored versions of the individual filters, so that combined in the convolution of these two filters, we actually have a linear phase property of our entire system. So the group delay is constant, which is always a good property. So this also verifies that our structure overall is working. This was all I wanted to show you here in this demo. You should take away from this how the efficient structure actually works, what some properties of the entire structure are, and why the structure is really that efficient. That concludes this exercise video. Thank you for watching.